Section 4.1 Equivalent Fractions. In this video we will see the definition of a fraction and what makes two fractions equivalent fractions, key observations about fractions, how to create equivalent fractions, the definition of a divisor and a greatest common divisor, how to find the greatest common divisor of two natural numbers, how to reduce a fraction to lowest terms, how to use the cancellation rule to reduce fractions, how to reduce fractions containing variables, how to deal with equivalent fractions of a higher denominator, and how to deal with fractions that are negative. In this section, we deal with fractions, numbers, or expressions of the form a over b. Fractions. A number of the form a over b where a and b are numbers is called a fraction. The number a is called the numerator of the fraction, while the number b is called the denominator of the fraction. Near the end of this section, we will see the numerator and denominator of a fraction can also be algebraic expressions, but for the moment we restrict our attention to fractions whose numerators and denominators are integers. We start our study of fractions with the definition of equivalent fractions. Equivalent fractions. Two fractions are equivalent if they represent the same numerical value. But how can we tell if two fractions represent the same number? Well, one technique involves some simple visualizations. Consider the image shown in Figure 4.1, where the shaded region represents 1/3 of the total area of the figure. One of three equal regions is shaded. In Figure 4.2, we've shaded 2/6 of the entire region. 2 of 6 equal regions are shaded. Then in Figure 4.3, we've shaded 4/12 of the entire region. 4 of 12 equal regions are shaded. Let's take the diagrams from 4.1, 4.2, and 4.3 and stack them on top the other, as shown in Figure 4.4. Figure 4.4 provides solid visual evidence that the following fractions are equivalent. 1 over 3 equals 2 over 6 equals 4 over 12. Key observations. If we start with the fraction 1 over 3, then multiply both numerator and denominator by 2, we get the following result. 1 times 2 is 2, and 3 times 2 is 6. So the result is 2 over 6. This is precisely the same thing that happens going from Figure 4.1 to 4.2, where we double the number of available boxes going from 3 available to 6 available, and double the number of shaded boxes going from 1 shaded to 2 shaded. If we start with the fraction 1/3, then multiply both numerator and denominator by 4, we get the following result. In the numerator, 1 times 4 is 4, and the denominator, 3 times 4 is 12, so the result is 4 over 12. This is precisely the same thing that happens going from Figure 4.1 to 4.3, where we multiply the number of available boxes by 4, going from 3 available to 12 available, and multiply the number of shaded boxes by 4, going from 1 shaded to 4 shaded. The above discussion motivates the following fundamental result: creating equivalent fractions. If you start with a fraction and multiply both its numerator and denominator by the same number, the resulting fraction is equivalent, has the same numerical value, to the original fraction. In symbols, a over b equals a times x over b times x. Arguing in reverse. Reversing the above argument also holds true. If we start with the fraction 2 over 6 and divide both numerator and denominator by 2, we get the following result. In the numerator, 2 divided by 2 is 1, and the denominator, 6 divided by 2 is 3, so we get 1 over 3. This is precisely the same thing that happens going backwards from Figure 4.2 to Figure 4.1, where we divide the numerator of available boxes by 2, going from 6 available to 3 available, and dividing the number of shaded boxes by 2, going from 2 shaded to 1 shaded. If we start with the fraction 4 over 12, then divide both numerator and denominator by 4, we get the following result. In the numerator, 4 divided by 4 is 1, and the denominator, 12 divided by 4 is 3, so the result is 1 over 3. This is precisely the same thing that happens going backwards from Figure 4.3 and to 4.1. Where we divide the number of available boxes by 4, going from 12 available to 3 available, and divide the number of a line of shaded boxes by 4, going from 4 shaded to 1 shaded. The above discussion motivates the following fundamental result: creating equivalent fractions. If you start with a fraction and divide both its numerator and denominator by the same number, the resulting fraction is equivalent, has the same numerical value to the original fraction in symbols. So a over b equals a divided by x over b divided by x. The greatest common divisor. We need a little more terminology. Divisor. If d and a are natural numbers, we say that d divides a. If and only if, when a is divided by d, the remainder is 0. In this case, we say that d is the divisor of a. For example, when 36 is divided by 4, the remainder is 0. In this case, we say that 4 is the divisor of 36. On the other hand, when 25 is divided by 4, the remainder is not 0. In this case, we say that 4 is not a divisor of 25. Greatest common divisor. Let a and b be natural numbers. The common divisors of a and b are those natural numbers that divide both a and b. The greatest common divisor is the largest of these common divisors. Example 1. Find the greatest common divisor of 18 and 24. Solution. First, list the divisors of each number. The numbers that divide each number with 0 remainder. The divisors of 18 are 1, 2, 3, 6, 9, and 18. The divisors of 24 are 1, 2, 3, 4, 6, 8, 12, and 24. The common divisors are 1, 2, 3, and 6. The greatest common divisor is the largest of the common divisors. That is, the greatest common divisor is 6. That is, the largest number that divides both 18 and 24 is the number 6. Reducing a fraction to lowest terms. First, a definition. Lowest terms. A fraction is said to be reduced to lowest terms if the greatest common divisor of both numerator and denominator is 1. Thus, for example, 2 over 3 is reduced to lowest terms because the greatest common divisor of 2 and 3 is 1. On the other hand, 4 over 6 is not reduced to lowest terms because the greatest common divisor of 4 and 6 is 2. Example 2. Reduce the fraction 18 over 24 to lowest terms. Solution. One technique that works well is dividing both numerator and denominator by the greatest common divisor of the numerator and denominator. In example 1, we saw that the greatest common divisor of 18 and 24 is 6. We divide both numerator and denominator by 6 to get. In the numerator, 18 divided by 6 is 3, and the denominator, 24 divided by 6 is 4, so the result is 3 over 4. Note that the greatest common divisor of 3 and 4 is now 1, thus 3 over 4 is reduced to lowest terms. There's a second way we can show division of numerator and denominator by 6. First, factor both numerator and denominator as follows. 18 factors into 3 times 6, and 24 into 4 times 6. You can then show division of both numerator and denominator by 6 by crossing out or canceling a 6 in the numerator for a 6 in the denominator, like this. So the 6's cancel, and we're left with 3 over 4, an equivalent fraction reduced to lowest terms. Important point. In example 2, we saw that 6 was both the divisor and a factor of 18. The words divisor and factor are equivalent. We use the following technique in our second solution, example 2, the cancellation rule. If you express numerator and denominator as a product, then you may cancel common factors from the numerator and denominator. The result will be an equivalent fraction. Because of the cancellation rule, one of the most effective ways to reduce a fraction to lowest terms is to first find prime factorizations for both numerator and denominator, then cancel all common factors. Example 3. Reduce the fraction 18 over 24 to lowest terms. Use factor trees to prime factor numerator and denominator. So factor 18 into 6 and 3, then 6 into prime factors 2 and 3. And 24 factor 24 into 4 and 6, and 4 into prime factors 2 and 2, and 6 into prime factors 2 and 3. Once we factor the numerator and denominator, we can cancel common factors. So 18 has prime factors 2, 3, and 3, and 24 has prime factors 2 times 2 times 2 times 3. They have a 2 and a 3 in common, so we'll cancel these, and we're left with 3 in the numerator and 2 times 2 in the denominator, and 2 times 2 is 4, so we're left with 3 over 4. Thus, 18 over 24 equals 3 over 4. Example 4. Reduce the fraction 28 over 42 to lowest terms. Use factor trees to prime factor numerator and denominator. 28 factors into 4 and 7, and 4 factors into 2 and 2. 42 factors into 6 and 7, and 6 factors into 2 and 3. So the prime factors of 28 are 2 times 2 times 7, and the prime factors of 42 are 2 times 3 times 7. Canceling what's common, they have a 2 in common and a 7 in common, so we're left with 2 in the numerator and 3 in the denominator. Thus, 28 over 42 equals 2 over 3. Reducing fractions with variables. We use exactly the same technique to reduce fractions whose numerators and denominators contain variables. Example 5. Reduce 56x squared y over 60x y squared to lowest terms. Solution. Use factor trees to factor the coefficients of numerator and denominator. So 56 factors into 4 and 14, 4 into prime factors 2 and 2, and 14 into prime factors 2 and 7. 60 factors into 6 and 10, 6 into prime factors 2 and 3, 10 into prime factors 2 and 5, and we'll cancel the common factors. So the prime factors of 56 were 2 times 2 times 2 times 7. The factors of x squared is x times x. And y is, there's just one factor of y. In the denominator, we have prime factors 2 times 2 times 3 times 5, x, and 2 factors of y. Canceling what's in common, they have 2 2's in common, an x in common, and a y in common, and we're left with 2 times 7 times x in the numerator, and 3 times 5 times y in the denominator. Simplifying this, 2 times 7 times x is equivalent to 14x, and 3 times 5 times y in the denominator is equivalent to 15y. Thus, 56x squared y over 60x y squared equals 14x over 15y. A word on mathematical notation. There are 2 types of mathematical notation, 1 inline mathematical notation and 2 displayed mathematical notation. Inline mathematical notation. The notation is called inline mathematical notation. When the same expression is centered on its own line, as in, this type of notation is called displayed mathematical notation. When you work a problem by hand using pencil and paper calculations, a preferred format is displayed notation, like the displayed notation used to simplify the given expression in example 5. However, computers and calculators require that you enter your expression using inline mathematical notation. Therefore, it is extremely important that you are equally competent with either mathematical notation, displayed or inline. By the way, order of operations, when applied to the inline expression, requires that we perform multiplication inside the parentheses first. Then we must perform multiplication divisions as they occur, as we move from left to right through the expression. This is why the inline notation is equivalent to the displayed notation. However, the expression is a different beast. There are no parentheses, so we perform multiplication division as they occur, moving left to right through the expression. Thus, we must first take the product of 14 and x, divide the result by 15, then multiply by y. In displayed notation, this result is equivalent to, which is a different result. Some readers might wonder why we did not use the notation to describe the solution in example 5. After all, this inline notation is also equivalent to the displayed notation. However, the point is that we don't need to, as order of operations already requires that we take the product of 14 and x before dividing by 15y. If this is hurting your head, know that it's quite acceptable to use the equivalent notation instead of Both are correct. Equivalent fractions and hierarchy of terms. Sometimes the need arises to find an equivalent fraction with a different, larger denominator. Example 6. Express 3 over 5 as an equivalent fraction having denominator 20. Solution. The key here is to remember that multiplying numerator and denominator by the same number produces an equivalent fraction. To get an equivalent fraction with a denominator of 20, we'll have to multiply the numerator and denominator of 3 over 5 by 4. Multiplying the numerator, 3 times 4 is 12. Multiplying the denominator, 5 times 4 is 20. Therefore, 3 over 5 equals 12 over 20. Example 7. Express 8 as an equivalent fraction having denominator 5. Solution. The key here is to note that 8 equals 8 over 1. Understood denominator is 1. To get an equivalent fraction with the denominator 5, we'll have to multiply numerator and denominator of 8 over 1 by 5. So in the numerator, 8 times 5 is 40, and the denominator 1 times 5 is 5. Therefore, 8 equals 40 over 5. Example 8. Express 2 over 9 as an equivalent fraction having denominator 18a. Solution. To get an equivalent fraction with a denominator of 18a, we'll have to multiply numerator and denominator of 2 over 9 by 2a. In the numerator, 2 times 2a is 4a, and the denominator, 9 times 2a, is 18a. Therefore, 2 over 9 equals 4a over 18a, or equivalently, with parentheses, around both numerator and denominator. Negative fractions. We have to also deal with fractions that are negative. First, let's discuss placement of the negative sign. Positive divided by negative is negative, so 3 divided by negative 5 equals a negative 3 over 5. But it's also true that negative divided by positive is negative, thus negative 3 over 5 equals negative 3 over 5. These two observations imply that all three of the following fractions are equivalent. The same number, 3 over negative 5 equals negative 3 over 5 equals negative 3 over 5. Note that there are three possible placements for the negative sign: the denominator, the fraction part, or the numerator. Any one of these placements produces an equivalent fraction. Fractions and negative signs. Let a and b be any integers. All three of the following fractions are equivalent. The same number, a over negative b equals negative a over b equals a negative a over b. Mathematicians prefer to place the negative sign either in the numerator or on the fraction bar. The use of a negative sign in the denominator is discouraged. Example 9. Reduce 50x cubed over negative 75x to the fifth to lowest terms. Solution. Prime factor, numerator, denominator cancel. So the numerator factors into 2 times 5 times 5 times 3 factors of x. And the denominator factors into negative 3 times 5 times 5 times 5 factors of x. The numerator and denominator have 2 5s and 3 x's in common, so we'll cancel all those, and we're left with 2 in the numerator and negative 3 times x in the denominator. Simplifying, we get 2 over negative 3x squared. However, it is preferred that there be no negative signs in the denominator, so let's place the negative sign on the fraction bar. The numerator would suit as well. Thus, 50x cubed over negative 75x to the fifth equals negative 2 over 3x squared. We also have the following result. Fractions and negative signs. Let a and b be any integers. Then negative a over negative b equals a over b. Example 10. Reduce negative 12xy squared over negative 18x squared y. Solution. Unlike example 9, some like to take care of the sign of the answer first. So since there's two negative signs, we can change this fraction to a positive. Now we can factor numerator and denominator and cancel common factors. So 12xy squared factors into 2 times 2 times 3 times x times 2 factors of y. And 18x squared y in the denominator factors into 2 times 3 times 3 times 2 factors of x times y. The numerator and denominator have a 2, 3, x and y in common, so we'll cancel those. And we're left with 2 times y in the numerator, 3 times x in the denominator, which simplifies to 2y over 3x. Thus, negative xy squared over negative 18x squared y equals 2y over 3x.